Demand Management Basics. Demand management is the gateway module in manufacturing planning and control, providing the link to the marketplace, other plants, warehouses, and other important customers. As such, it is in demand management that we gather information from and about the market, doing things like forecasting customer demand, entering orders, and determining specific product requirements. The position of demand management in the manufacturing planning and control system is shown in this figure. It is the key connection to the market in the front end of the MPC system. The external aspects of the demand management module are depicted as the double-ended arrow connected to the marketplace outside the MPC system. This simply underscores the need to communicate with the customers as well as to gather information from and about them. The other linkages are with the sales and operations planning and the master production schedule modules. The information provided to S&OP is used to develop sales and operations, including manufacturing plans, covering a year or more in duration at a fairly high level of aggregation. Both forecast and actual demand information is provided to the Master Production Schedule module. It is in this module that short-term, product-specific manufacturing plans are developed and controlled as actual demand becomes available, and information is provided to provide delivery promises and order status to customers. It is through these linkages that quantities and timing for all demands must be collected and coordinated with the planning and control activities of the company. The planning part of manufacturing planning and control involves determining the capacity that will be made available to meet actual future demands for products. Much of this planning activity occurs in the sales and operations module. The control part determines how the capacity will be converted into products as the orders come in. The company executes the plan as actual demand information becomes available. The control function determines how the company will modify the plans in light of forecast errors and other changes in assumptions that inevitably occur. For many firms, planning the execution and controlling demand, quantities, and timings are a day-to-day interactive dialogue with customers. For other companies, particularly in the process industries, the critical coordination is in scheduling large inter- and intra-company requirements. For others, physical distribution is critical, since the factory must support a warehouse replenishment program, which can differ significantly from the pattern of final customer demand. The difference between the pattern of demand and the response by the company points out the important distinction between forecasts and plans. In demand management, forecasts of the quantities and timing of customer demand are developed. These are estimates of what might occur in the marketplace. Manufacturing plans that specify how the firm will respond are based on these forecasts. This distinction between forecasts and plans is important for two reasons. First, a manager cannot be held responsible for not getting a forecast right. We can and should hold managers responsible for making their plans, however. The second reason for making a distinction between the plan and the forecast is the demands of customers are the independent demands. When and if a customer decides to buy our product, that decision is independent of the action of the company. Obviously, we can influence the timing and quantities through advertising, pricing, promotions, and so on, but the ultimate decision rests with the customer. On the other hand, if we have plans for building a product at a constant rate throughout the year, the demand for some parts that are needed can be calculated. The demand for the parts depends on our plans for producing the product. It is dependent demand. Similarly, the demand from our warehouses for product depends on our plans for replenishing the warehouses. When conditions change, the plans may need to change, and this in turn could change the dependent demands that need to be coordinated in the demand management module. The linkage between demand management, S&OP, and master production scheduling in the front end makes clear the importance of providing complete forecasts and providing them at the appropriate level of detail. The importance of identifying all sources of demand is obvious but sometimes overlooked. If material and capacity resources are to be planned effectively, we must identify all sources of demands: spare parts, distribution, inventory changes, demonstration stock, new items, promotions, and so on. Only when we have accounted for all demand sources, we can develop realistic manufacturing planning and control plans. Demand management activities must conform to the strategy of the company, the capabilities of manufacturing, and the needs of customers. Different strategies, capabilities, and customer needs define different manufacturing planning and control environments within which demand management activities are carried out. In order to understand how the activities might differ from the environment to environment, we first develop a broad classification of manufacturing environments. Key to this classification is the concept of the customer order decoupling point, or as it is called sometimes, the order penetration point. The customer order decoupling point can be looked at as the point at which demand changes from independent to dependent. It is the point at which the firm, as opposed to the customer, becomes responsible for determining the timing and quantity of material to be purchased, made, or finished. The figure here provides a means for visualizing the customer order decoupling point as it might move from finished goods inventory through the company all the way back to the supplier. The different locations of the customer order decoupling point give rise to different categories of manufacturing environments. Companies that serve their customers from finished goods inventory are known as make-to-stock. Those that combine a number of options together to meet a customer's specifications are called assemble-to-order firms. Others that make the customer's product from raw materials, parts, and components are make-to-order firms. An engineer-to-order firm will work with the customer to design the product, then make it from purchased materials, parts, and components. Of course, many firms will serve a combination of these environments, and a few will have all simultaneously. In our course, we will consider the engineer-to-order and make-to-order environments together. Now let's explain those environments and their characteristics. First is make-to-stock environment. In this environment, the key focus of the demand management activities is on the maintenance of finished goods inventories. In this environment, the customers buy directly from the available inventory, so customer service is determined by whether their item is in stock or not. A key aspect of the management of the finished goods inventory is the determination of when, how much, and how to replenish the stock at a specific location. This is the physical distribution concern in demand management. This can be an extremely broad concern encompassing numerous locations in many countries and involving several levels of distribution and storage. Some make-to-stock firms employ plant warehouses, distribution centers, local warehouses, and even vendor-managed inventory inside their customers' locations. Management of this supply chain requires information on the status of inventory in the various locations, relationships with transportation providers, and estimates of the customer's demands by location and item. The essential issue in satisfying customers in the make-to-stock environment is to balance the level of inventory against the level of service to the customer. If unlimited inventory were possible and costless, the task would be trivial. Unfortunately, this is not the case. Providing more inventory increases costs, so a trade-off between the cost of the inventory and the level of customer service must be made. The trade-off can be improved by better estimates of customer demand, by more rapid transportation alternatives, by faster production, and by more flexible manufacturing. Let's continue with assemble-to-order environment. There are many manufacturing examples that exist using this environment. You may have experienced this yourself when you ordered a personal computer. You decide what components you want, and the company assembles components to complete your order. Many people buy their cars in this way, and some industrial products are assembled to meet the user specifications. In the assemble-to-order environment, the primary task of demand management is to define the customer's order in terms of alternative components and options. For example, a 2-door versus 4-door car, with or without anti-lock brakes, and so on. It is also important to assure that they can be combined into a viable product in a process known as configuration management. This is a critical step because it might not be possible to assemble certain combinations. One of the capabilities required for success in this environment is engineering design that enables as much flexibility in combining components, options, and modules into finished products as possible. The assemble-to-order environment clearly illustrates the two-way nature of the communication between customers and demand management. Customers need to be informed of the allowable combinations, and the combinations should support marketplace desires such as sports trim for cars, for example. Moreover, customers' orders must be configured, and the customers must be informed of the delivery date of the finished product. In this environment, the independent demand for the assembled items is transformed into dependent demand for the parts required to produce the components needed. The inventory that defines customer service is the inventory of components, not the inventory of finished products. There are some significant advantages from moving the customer order decoupling point from finished goods to components. For example, the number of finished products is usually substantially greater than the number of components that are combined to produce the finished goods. Make or engineer to order environment. The focus of demand management in the make-to-stock and assemble-to-order was largely on satisfying customers from the appropriate inventory, finished goods or components. In make-to-order and engineer-to-order environments, there is another resource that needs to be taken into account, and this is engineering. Moving the customer order decoupling point to raw materials or even suppliers puts independent demand information further into the firm and reduces the scope of dependent demand information. Moreover, the nature of the information needed from customers changes. We know what the customers could buy in the make to stock and available to order, but not if, when, or how many. In the make or engineer to order environment, on the other hand, we are not sure what they are going to buy. We need, therefore, to get the product specifications from the customers and translate these into manufacturing terms in the company. This means that a task of demand management in this environment is to coordinate information on customers' product needs with engineering. The need for engineering resources in the engineer-to-order case is somewhat different from that in the make-to-order case. In the make-to-order environment, engineering determines what materials will be required, what steps will be required in manufacturing, and the costs involved. The materials can come from the company's inventory or be purchased from suppliers. In the engineer-to-order environment, more of this same information is needed from customers, although more of the detailed design may be left to the engineers than the customer. Because of the need for engineering resources in this environment, demand management's forecasting task now includes determining how much engineering capacity will be required to meet future customer needs. This may be complicated because some orders can be in progress even though they aren't completely specified and engineered, so material coordination is still important. Although there is certainly some overlap among them, a summary of the major tasks in the demand management for each of the environments is provided in this picture. The customer order decoupling point could actually be with the supplier in the engineer-to-order case. In all the environments, suppliers' capabilities may limit what we are able to do, so coordination with them is essential. This span of involvement from customer to supplier gives a rise to the term supply chain, or sometimes called the demand chain, and the coordination of activities along the supply chain, referred to supply chain management. A key element of the demand management module is providing the information to help balance the supply of products with the demand. Gathering intelligence on actual conditions in the marketplace provides the basis for deciding whether to change the company's plans. We will see later in the forecasting section the use of pyramid forecasting to harmonize various forecasts, other sources of information on the market, and company goals. At times, this process will leave some potential demand unfulfilled. There are a lot of legitimate reasons for this. Investments in capacity may not be warranted. Some product lines may not be sufficiently profitable, or key materials may be in short supply. At this time, real management discipline is required. Purposely leaving some demand on the table is extremely difficult. A pleading customer is hard to turn away. Perhaps the most important activity in demand management is to be honest with customers. In our experience, customers prefer honest answers, even if they are unpleasant, than inaccurate information. A demand management model with discipline in the management and effective systems provides the basis for honest communication with customers. They can be told when to expect delivery or when inventory will be replenished, and they can count on it. Providing the basis for honest communication with customers can pay handsome dividends in terms of customer loyalty. Collaborative planning, forecasting, and replenishment represents a major enhancement of the principles of demand management. This approach is a recent innovation for dramatically improving communications between customers and suppliers in forecasting product demand. It is based on making organizational changes in both customer and supplier companies to improve communication and collaboration, developing new business processes for creating forecast information, and introducing daily communication between companies of a shared forecast. This can benefit both the customer and the supplier by helping increase sales and fill rates while at the same time reducing inventories. This approach is especially powerful when one or a few customers represent a large portion of a supplier's businesses. Here is a 9-step collaborative planning, forecasting, and replenishment process model that provides a general framework for companies interested in implementing this approach. This framework provides retailers and suppliers with general guidelines for sharing key supply chain information and coordinating their plans. Under this approach, supply chain partners develop one consensus forecast. This forecast can be developed collaboratively, or one of the partners can provide an initial forecast that is then used as the basis for developing a collaborative forecast. Once the collaborative forecast is developed, then the supply chain partners can go about optimizing the activities of their companies. As a result, production schedules can then be developed by the supplier based on the actual demand at the retailer. In this section, we're going to talk about forecasting demand. Forecasts are estimates of the occurrence, timing, or magnitude on uncertain future events. Forecasts are essential for the smooth operations of business organizations. They provide information that can assist managers in guiding future activities toward organizational goals. Operations managers are primarily concerned with forecasts of demand, which are often made by marketing or in conjunction with marketing. However, managers also use forecasts to estimate raw material prices, plan for appropriate levels of personnel, help decide how much inventory to carry, and a host of other activities. This results in better use of capacity, more responsive service to customers, and improved profitability. There are some variables in forecasting decisions. Forecasting activities are a function of the type of forecast, the demand, technological, the time horizon, short, medium, or long range, the databases available, and the methodology employed, qualitative or quantitative. Forecasts of demand are based primarily on non-random trends and relationships with an allowance for random components. Forecasts for groups or products tend to be more accurate than those for single products, and short-term forecasts are more accurate than the long-term forecasts. Quantification also enhances the objectivity and precision of a forecast. There are numerous of forecasting depending on the need of the decision maker. These types of methods can be categorized in two ways: opinion and judgmental methods or qualitative methods, time series or quantitative forecasting methods. Some opinion and judgment forecasts are largely intuitive, while others integrate data and perhaps even mathematical or statistical techniques. Judgmental forecasts often consist of forecasts by individual salespeople, forecasts by division or product line managers, and combined estimates of the two. Historical analogy relies on comparisons. Delphi relies on the best method from a group of forecasts. All these methods can incorporate experiences and personal insights. However, results may differ from one individual to the next, and they are not all amendable to analysis. So there may be little basis for improvement over time. In the next several lectures, we are going to explore time series or quantitative forecasting methods. Let's continue with time series methods. A time series is a set of observations of a variable at regular intervals over time. In decomposition analysis, the components of a time series are generally classified as trend, cyclical, seasonal, and random or irregular. Note that autocorrelation effects are sometimes included as an additional factor. Time series are tabulated or graphed to show the nature of the time dependence. The forecast value, Ys, is commonly expressed as a multiplicative or additive function of its components. Examples here we are going to see later will be based upon the commonly used multiplicative models. Here are the formulas. Trend is a gradual long-term directional movement in the data, growth or decline. Seasonal effects are similar variations occurring during corresponding periods. For example, December retail sales. Seasonal can be quarterly, monthly, weekly, daily, or even hourly indexes. Cyclical factors are the long-term swings about the trend line. They are often associated with business cycles and may extend out to several years in length. Random components are sporadic, unpredictable effects due to chance and unusual occurrences. They are the residual after the trend. Cyclical and seasonal variations are removed. Here is a simple procedure for forecasting. The first step, plot historical data to confirm relationship, linear, exponential, etc. Develop a trend equation to describe the data. Develop a seasonal index, for example, monthly index values. Project trend into the future. Multiply trend values by corresponding seasonal index values. Modify projected values by any knowledge of cyclical business conditions or anticipated irregular effects. There are three methods that describe the trend: moving average, hand-fitting, and least squares. Moving average. A centered moving average is obtained by summing and averaging the values from a given number of periods repetitively, each time deleting the oldest value and adding a new value. Moving averages can smooth out fluctuations in any data while preserving the general pattern of the data. Longer averages result in more smoothing. However, they do not yield a forecasting equation, nor do they generate values for the ends of the data series. Here is the formula for moving average. A weighted moving average allows some values to be emphasized by varying the weights assigned to each component of the average. Weights can be either percentages or a real number. Now let's see an example. This is the first example in this lecture, how to calculate moving average and weighted moving average. Shipments in tons of a raw material are shown in the following table for the first 11 years. We have to compute the 3-year moving average and use it to forecast shipments in year 12. And second, using a weight of 3 for the most recent data, 2 to the next, and 1 for the oldest, forecast shipments in year 12 by using moving weighted average. For the first calculation, I have put a formula here which sums the first 3 periods, because we have to use 3-year moving average, and divide it by 3. So we find 3.7 tons for the year 4. If I drop this down to the year 12, I will find 17, which will be the forecast using a 3-year moving average for shipments in year 12. And the second, we have to use a weight of 3 for the most recent data, which in this case is year 11. 3, 2, and 1 for the oldest. So here I have put the formula from the lecture. We have the sums multiplied tons and weights, and then divided by the sum of the weights. We receive 17.8 tons using weighted moving average with these weights here. Now let's get back to the lecture. Next method is hand fitting. A hand fit or freehand curve is simply a plot of a representative line that subjectively seems to best fit the data points. For linear data, the forecasting equation will be of this form: YC equals A plus B multiplied by X signature, where YC is the trend value, A is the intercept, where a line crosses the vertical axis, and B is the slope, the rise, or delta Y divided by the run delta X, and X is the time value, years, quarters, etc. The signature identifies the points in time when X is 0, as well as the X and Y units. Let's see a practical example how this works. Here is the example. Use a hand-fit line to develop a forecasting equation for the data in the table, and use the equation to forecast raw material shipment for year 12. Okay, so this works in this way. We first have to select points some distance apart. A straight line connecting the values, for example, for years 3 and 8, I think might be good, but you can choose any other period. Freehand representation of the data. From this, we can determine the slope and intercept. The calculation for the slope is in this formula: the end period and the beginning period. We have the tons and the years divided. We receive 1.6 tons. The intercept A, we estimated at 0.5, but you can estimate it at 1 or 1.2 as well. This is an estimation. So the equation will have this form: YC 0.5 plus 1.6 multiplied by X, which is the year. So using this equation for year 12, we just have to multiply the slope by the year. And the forecast for raw materials in year 12 will be 19.7 tons using this method. Now let's get back to the lecture and to explore least squares method. Least squares are a mathematical technique of fitting a trend to data points. The resulting line of best fit has the following properties. The summation of all vertical deviations about it is 0, and the summation of all vertical deviations squared is a minimum, and third, the line goes through the means X and Y. For linear equations, the line of best fit is found by the simultaneous solution for A and B of the following two normal equations. Those equations can be used in the form shown here and are used in that form for regression. However, with time series, the data can also be coded so that the sum of x's equals 0. Two terms then drop out and the equations are simplified to the following. To code the time series data, we have to designate the center of the time span as x equals 0 and let each successive period be plus minus one more unit away. For example, for an even number of periods, we can use values of plus minus 0.5, 1.5, 2.5, etc. Now let's see practical examples to see how this method works. This is the example using the least squares method. We will use it to develop a linear trend equation for the same data we used for the previous example. Also, we have to calculate the trend value for year 16. So I have put a different table here, the years X year coded. So this is as we explained from plus minus 1, 2, 3, 4, 5 in the lecture. Also we have Y shipments. Here the sum is 0. X year coded should be 0. Y shipments. And here are simple formulas to find X multiplied by Y. Dropped down. And also X squared. Also drop down, so we will receive all those values. For dA, the formula is the sum of y's divided by their number. In this case, the sum is 113 divided by 11. We have 11 periods. B is the sum of X multiplied by Y divided by the sum of X squared. Here is the formula, very simple calculations, and we can develop the equation in this form. 10.3 plus 1.6 multiplied by X, where X is the year and Y are the tons. So for year 16, we will have 10.3 plus 1.6 multiplied by 16, because we are looking for the trend value for year 16, and we will receive 35.9 tons will be the forecast or trend value for year 16. Let's wrap up this lecture with seasonal indexes. A seasonal index is a ratio that relates a recurring seasonal variation to the corresponding trend value at a given time. In the ratio to moving average method of calculation, monthly or quarterly data are typically used to compute a 12-month or 4-quarter moving average. This dampens out all seasonal fluctuations. Actual monthly or quarterly values are then divided by the moving average value centered on the actual month. In the ratio to trend method, the actual values are divided by the trend value centered on the actual month. The ratios obtained for several of the same months or quarters are then averaged to obtain the seasonal index values. Let's continue with another method, exponential smoothing. Exponential smoothing is a moving average forecasting technique that weights past data in an exponential manner so that most recent data carry more weight in the moving average. With simple exponential smoothing, the forecast ft is made up of the last period forecast f t-1 plus a portion alpha of the difference between the last period's actual demand a t-1 and last period forecast f. The smoothing constant alpha is a number between 0 and 1 that enters multiplicatively into each forecast, but whose influence declines exponentially as the data become older. Typical values range from 0.01 to 0.4. Low alpha gives more weight to the past data, the past average, and will effectively dampen high random variations. At the same time, high alpha values are more responsive to changes in demand, from new product introduction, promotional campaigns, etc. An alpha of 1 would reflect total adjustment to recent demand, and the forecast would be last period's actual demand. A satisfactory alpha can generally be determined by trial and error modeling on computer to see which values minimizes forecast errors. Sample exponential smoothing yields only an average. It does not extrapolate for trend effects. No alpha value will fully compensate for a trend in the data. An alpha value that yields an approximately equivalent degree of smoothing as a moving average of n periods is found by this formula. Alpha equals 2 divided by n plus 1. Now let's see a practical example how to use exponential smoothing. Here is the example. A firm uses simple exponential smoothing with coefficient alpha 0.1 to forecast demand. The forecast for the week of February 1 was 500 units, while actual demand turned out to be 450 units. Forecast the demand for the week of February 8. So here is the data: actual demand, old forecast, and the new forecast. Here I have put the formulas: the forecast error, the correction using the coefficient, and the new forecast. This is the old forecast plus the correction. So for the second period, I have to just drag the formula down, and I will receive the forecast error 10, correction 1, and the new forecast will be 496 units. Then the second, assume that the actual demand during the week of February 8 turned out to be 505. So forecast the demand for the week of February 15. We will use the same formula, and we will receive that the new forecast will be 2 units more. And now we can continue forecasting in this way through March 15, assuming that subsequent demands were 516, 488 to 510 units. So this is done period by period. I have put all the data in the table, but basically you should do it period by period. So if I drag down at once the same formula, and we will get the full picture: the new forecast, the old forecast, and actual demand. This was everything for this lecture. See you in the next one. In this next lecture, we are going to explore the regression and correlation methods. Regression and correlation techniques quantify the statistical association between two or more variables. The simple regression expresses the relationship between a dependent variable y and an independent variable x in terms of the slope and intercept of the line of best fit relating the two variables. Simple correlation expresses the degree or closeness of the relationship between two variables in terms of a correlation coefficient that provides an indirect measure of the variability of points from the line of best fit. Neither regression nor correlation gives proof of a cause and effect relationship. Let's start with the regression. The simple linear regression model takes the form of yc equals a plus b multiplied by x. This is from the previous lectures, where yc is the dependent variable and x the independent variable. Values for the slope b and intercept a are obtained by using the normal equations written in the convenient forms. In those equations, x bar and y bar are the means of the independent and dependent variables respectively, and n is the number of pairs of observations made. Standard deviation of regression. A regression line describes the relationship between a given value of the independent variable x and the mean of the corresponding probability distribution of the dependent variable y. We assume the distribution of y values is normal for any given x value. The point estimate or forecast is the mean of that distribution for any given value of x. The standard deviation of regression, S, is a measure of the dispersion of data points around the regression line. For simple regression, the computation of S has n-2 degrees of freedom. Here is the formula that we use to compute the standard deviation of regression. Now let's see a practical example how to use this method. Here is the example. The general manager of a building materials production plant feels that the demand for plasterboard shipments might be related to the number of construction permits issued in the country during the previous quarter. The manager has collected the data shown in the table. We have the number of permits and shipments for these 8 periods. First, compute values for the slope B and intercept A. So here we have 8 pairs of observations. This means that we will find X and Y bar. X bar is the number of permits divided by 8, and Y bar is the number of shipments, the sum of shipments divided by the number of observations. So using those formulas here from the lecture, then we can calculate B and A. This is a bit complex formula, but you can explore it later. It uses the same formulas from the lecture, just I have put all those cells here in the formula. We can calculate B and then A. We use a Y bar, B, X bar, and we find those values for B and A. Second, determine a point estimate for plasterboard shipments when the number of construction permits is 30. Now we make the regression equation. YC is 0.91, which is A, plus B multiplied by X. And if X is 30, the number of construction permits, when we calculate here, we will find 13 shipments will be required. The third thing is compute the standard deviation of regression. Here again, we will use this a bit complex formula, but here I have done it for you using the Excel formula bars, and after substituting all the values, we find 2.2 shipments in the standard deviation of regression. In the next lecture, we are going to explore the simple correlation methods. Let's continue with the simple correlation method. The simple linear correlation coefficient R is a number between -1 and +1 that tells how well a linear equation describes the relationship between two variables. As illustrated in this picture, R is designated as positive if Y increases as X increases, and negative if Y decreases as X increases. An R of 0 indicates an absence of any relationship between the two variables. The deviation of all points Y from the regression line YC consists of deviation accounted for by the regression line and random deviation. This figure here illustrates this for one point Y. Squaring the deviation, we have variation. Total variation equals explained plus unexplained, and here is the formula. The coefficient of determination R squared is the ratio of explained variation to total variation. The coefficient of correlation R then is the square root of the coefficient of determination. When the sample size is sufficiently large, greater than 50, the value of R can be computed more directly from this formula, which is a bit complex, but we will see now an example. Okay, now let's see the example. A study to determine the correlation between plasterboard shipments X and construction permits Y revealed the following data. This data can be found from the previous example. Also, you can put different numbers to find a regression and correlation coefficients. So compute the correlation coefficient. This is the complex formula from the lecture, and here I have entered it for you using the Excel formula bars. So basically you can use this formula, and from the previous lecture example as well. They are ready to use for you, and this calculates the correlation coefficient 0.9. Here you can put different numbers as well, also in the previous example. What does coefficient mean? The significance of any value of R can be statistically tested under a hypothesis of no correlation. To test, the computed value of R is compared with a tabled value of R for a given sample size and significance level. If the computed level exceeds the tabled value, the correlation is significant. We will continue in the next 2 lectures, and we'll learn how to calculate forecast errors, and we'll see some more applications of those methods by practical examples. Let's continue with forecast controls. A simple measure of forecast error is to compute the deviation of the actual from the forecast values. Deviations will vary from plus to minus, but they should tend to average out near zero if the forecast is on target. Forecast error is the actual demand minus forecasted demand. The individual forecast errors are usually summarized in a statistic such as average error, mean squared error, or mean absolute deviation. Here is the formula for mean absolute deviation. To estimate, the estimate of the mean absolute deviation can be continually updated by using an exponential smoothing technique. In this way, the current mean absolute deviation can be calculated using this formula, where alpha is the smoothing constant. Higher values of alpha will make the current mean absolute deviation more responsive to current forecast errors. When the average deviation is divided into the cumulative deviation, the result is a tracking signal. Tracking signals are one way of monitoring how well a forecast is predicting actual values. They express the cumulative deviation, also called the running sum of forecast error, in terms of the number of average deviations. Action limits for tracking signals commonly range from 3 to 8. When the signal goes beyond this range, corrective actions may be required. Control charts are a second way of monitoring forecast error. Variations of actual from forecast or average values are quantified in terms of the estimated standard deviation of forecast SF. We can find it using this formula. Control limits are then set perhaps at 2 or 3 standard deviations away from the forecast average X bar, or the 2SF or 3SF limits are used as maximum acceptable limits for forecast error. Note that the limits are based on individual forecast values, so you assume that the errors are normally distributed around the forecast average. Now let's see a practical example for mean absolute deviation. Here is the example. A high-value item has a tracking signal action limit of 4 and has been forecasted as shown in the following table. In the table we have all the data, the period, actual, demand forecasted, different types of errors. We need to compute the tracking signal and indicate whether some corrective action is appropriate, and secondly, to compute the standard deviation of the forecast control limits. First, we calculate the mean absolute deviation. which is the total of error, the absolute value of the error, the sum, 60 divided by the number of periods, which is 10, and then the tracking signal is 36 divided by the mean absolute deviation 10, 3.6. In this case, the action limit given of 4 is not exceeded, which means that no additional action is necessary. Now let's continue with the control limits. Here is the formula. We talk about it in the lecture. So first we need to calculate the mean, the x bar, which is 80. This is the average of forecast, the values of the forecast. And then using the formula for the square root, we have the actual minus forecast divided by the number of periods minus 1. Here for the actual minus forecast, we use the value of 794, which gives us 13. And then the standard deviation of the forecast control limits, using the formula, it is 80 plus minus 2 times 13, or 54 to 106, and these values are rounded to integer values. We'll finish this section with this lecture forecast application, where we are going to explore 3 more practical examples as well. Forecast should be sufficiently accurate to plan for future activities. Low accuracy methods may suffice. Higher accuracy usually costs more to design and implement. Long-term forecasts used for location, capacity, and new product decisions require techniques with long-term horizons, while short-term forecasts, such as those for production and inventory control, labor levels, and cost controls, can rely more on recent history. Now let's explore 3 more examples related to demand forecasting. Okay, so this is the first example. As you can see, I have put the formulas here in advance, so you can use it right away. You have just to put different data here, or your own data from your company, so those sheets are ready to use for you. A food processing company uses a moving average to forecast next month's demand. Past actual demands in units are shown in this table, the months and the actual demands. First, compute a simple 5-month moving average to forecast demand for month 52. Here is the formula from the lectures. We have the sum of x's from the previous 5 periods divided by the number, because we have to use a simple 5-month moving average. We can use 3-month or 6-month, so we just have to put different periods here, their total, and to divide by the number of periods. In this case, is 126 units. The second, compute a weighted 3-month moving average, where the weights are highest for the latest months and descend in order of 3, 2, and 1. So here are the weights, and we use also the formula here. We have to sum the actual demand multiplied by the weights, their respective weights, and to divide by the sum of the weights. So in this case it is 6, 133 units. So here we can put different weights, for example, 5, 3, and 1. So you can see that the forecast has been changed. Let's continue with the next example. Okay, quarterly trend values for units demanded have been computed as for quarter 1, 620, quarter 2, 655, quarter 3, and quarter 4, 690 and 725 respectively. The corresponding seasonal indexes for the quarters are 0.72, 1.33, 1.05, and 0.9 respectively. Forecast the actual seasonalized sales for quarters 3 and 4. So here is the solution. Also the formulas, the seasonal, it's very simple formulas. The seasonal indexes are multiplied by the trend values, which are being computed in advance. So for quarter 3 it gives 725 units, and for quarter 4 653 units. And the last example is here. ABC Hospital has used a 9-month moving average forecasting method to predict drug and surgical dressing inventory requirements. The actual demand for one item is shown in the table, months and the demand. Using the previous moving average data, convert to an exponential smoothing forecast for month 33. Okay, so here is the solution. The moving average is the sum of the demand divided by the number of periods. In this case, the number of periods is 9. It's 78 units. Thus, assuming the previous forecast was, in this period, ft-1, 78. We will calculate alpha, which is 2, divided by n plus 1. In this case, n plus 1 is the number of periods 9 plus 1, 2 divided by 10. So, by using this formula, we can calculate the exponential smoothing forecast for month 33. And here also you see the formula, 78 plus the coefficient, then we have the last period demand 73 minus the moving average. So we receive 77 units. That was all for this section. This was the last lecture. So feel free to use all those formulas. They are ready for use. You don't have to put them into Excel. You just can use them as they are. See you in the next lectures. Sales and operations planning provides the key communication links for top management to coordinate the various planning activities in a business. These linkages are shown in this picture. For example, marketing initiatives dealing with the entry of a new product in the market can be coordinated with an increase in manufacturing capacity to support the marketing promotional plans. At the same time, financial resources are coordinated to support the working capital for the buildup of pipeline inventories. From a manufacturing perspective, sales and operations planning provides the basis to focus the detailed production resources to achieve the firm's strategic objectives. The sales and operations plans provide the framework within which the master production schedule is developed. Subsequent master production schedule decisions can be planned and controlled, and material resources and plant capacities can be coordinated in ways that are consistent with strategic business objectives. There are 4 fundamentals in sales and operations planning: demand, supply, volume, and mix. Now let's consider first the balance between demand and supply. When demand exceeds supply, customer service suffers because manufacturing cannot provide the volume of products required by the customer. Costs increase because of overtime and premium freight rates, and quality suffers because of the rush to ship products, all of which are unfavorable to the business. Likewise, when supply exceeds demand, the effect on the business is unfavorable. Inventories increase because of the imbalance between demand and manufacturing capacity. Layoffs result from production rate cuts, causing plant efficiency and morale to decline, and profit margins are squeezed because of price cuts and discounting. Therefore, the key to good business performance is to maintain a proper balance between demand and supply. It is important to have business processes in place to maintain a proper balance between demand and supply, and to provide early warning signals when they are becoming unbalanced. This is the role of sales and operations planning, and it can be accomplished through the effective coordination of the plans of the different functional areas in a business with the active involvement of top management. Two other fundamentals are volume and mix. These need to be treated separately in managing the manufacturing, planning, and control functions. Volume concerns big picture decisions about how much to make and the production rates for product families, while mix concerns detailed decisions about which individual products to make, in what sequence, and for which customer orders. What happens in many companies is that the focus is on mix decisions because these are urgent as a result of customer pressures. Volumes are only considered once a year when the business plan is developed and production rates must be fixed to establish overhead absorption. These companies don't spend enough time forecasting and planning their volumes. Instead of focusing on the big picture, they focus on the details in trying to predict mix. Smart companies carefully plan their volumes first and then focus on the mix decisions. This is done because if volumes are planned effectively, mix decisions become much easier to cope with. These companies find that imbalances in demand and supply occur frequently over time, over the course of a year, and as a result, volume decisions need to be reviewed and adjusted on a monthly basis. Sales and operations planning is concerned with getting the big picture right and then attending to the details and manufacturing planning and control. The role of sales and operations planning is to balance demand and supply at the volume level. Volume concerns rates, overall sales rates, production rates, aggregate inventories, and order backlogs. Once volume, rates, and level is effectively planned, the problem of mix, individual products, and orders become easier to cope with. Understanding the fundamentals of sales and operations planning makes this function easier to understand as a part of a company's manufacturing, planning, and control system. The operations portion of the sales and operations plan states the mission manufacturing must accomplish if the firm's strategic objectives are to be met. How to accomplish the operations plan in terms of detailed manufacturing and procurement decisions is a problem for manufacturing management. Within an agreed-on operations plan, the job in manufacturing is to hit the operations plan. Similar job definitions hold for sales and marketing and finance. This figure here also indicates that the planning in other manufacturing planning and control system functions is necessarily detailed, and the language is quite different from that required for the operations plan. The operations plan is normally stated in terms of aggregate units of output per month, while the master production schedule is stated in terms of end products units per week. The master production schedule might be stated in units that use special bills of materials to manage complicated options and do not correspond to the units used to communicate with top management. The operations plan needs to be expressed in meaningful units, but it also needs to be expressed in a manageable number of units. Experience indicates that 6 to 12 family groups seem to be about right for a top management group to handle. Each family grouping has to be considered in terms of expectations on sales, manufacturing, and the resultant inventories and backlogs. The cumulative result expressed in monetary units also has to be examined and weighed against overarching business plans. It is difficult to do sales and operations planning at the top of the pyramid here because there is not enough granularity at that level on which to base the demand and supply decisions. Likewise, at the bottom of the pyramid there is too much detail and it will be difficult to see an overall picture of volume in aggregate planning. The operations plan is not a forecast of demand. It's the plant production stated on aggregate basis for which manufacturing management is to be held responsible. The operations plan is not necessarily equal to a forecast of aggregate demand. For example, it may not be profitable to satisfy all the demand in a peak monthly period, but the production would be leveled over the course of seasonal cycle. The operations plan is a result of the sales and operations planning process. Inputs to the process include sales forecasts, but these need to be stated on the basis of shipments, not bookings, so that the inventory projections match physical inventories, and so that manufacturing goals are expressed correctly with respect to time. The most fundamental linkage here is that to master production schedule, which is a disaggregation of the operations plan. The result drives the detailed scheduling through detailed material planning and other manufacturing planning and control functions. The master production schedule must be kept in concert with the operations plan. As the individual daily scheduling decisions to produce specific mixes of actual end items and options are made, we must maintain parity between the sum of the manufacturing of the master production schedule quantities and the operations plan. If the relationship is maintained, then hitting the schedule means the agreed on operations plan will be met as well. Another critical linkage shown here is the link with demand management. Demand management encompasses order entry, order promising, and physical distribution coordination, as well as forecasting. This function must capture every source of demand against manufacturing capacity, such as inter-plant transfer, international requirements, and service parts. The other direct manufacturing planning and control linkage to sales and operations planning is with resource planning. This activity encompasses long-range planning of facilities. Involved is the translation of extended operations plans into capacity requirements, usually on a gross or aggregate basis. Resource planning is directly related to operations planning, since in the short term the resources available provide a set of constraints to operations planning. In the longer run, to the extent that operations plans call for more resources than available, financial appropriations are indicated. A key goal of the linkage between operations and resource planning is to answer what-if questions. Maintaining current resource planning factors related to the product groupings used for planning is the basis for performing this analysis. Sales and operations planning involves making decisions on each product family concerning changes to the sales plan, the operations plan, and the inventory or backlog. These decisions are made on the basis of recent history, forecasts, and the recommendations of middle management and top management's knowledge of business conditions. A formal process for accomplishing sales and operations planning is shown in this picture. This process begins shortly after a month's end and continues for some days. These steps involve middle management and others throughout the company, as well as top management. Now let's explore those steps of this sales and operations planning process. First step, run the sales forecasting reports. This step occurs shortly after the month end and involves the Information Systems Department updating the files with data from the month just ended, actual sales, production, inventories, and so on. This information is disseminated to the appropriate people and forms the basis for sales and marketing people to use in developing sales analysis, report, and changes to sales forecasts. Demand planning phase, step 2. The information received in the first step for new and existing products is reviewed by sales and marketing and discussed with the view of generating a new management forecast covering the next 12 or more months. For example, in the case of consumer make-to-stock products, price changes, competitive activity, economic conditions, and field sales input regarding large customers are considered in revising the sales forecast. Here the task is to override the statistical forecast when appropriate and to bring senior marketing and sales management into the loop. It is also necessary to consider the new forecast along with the actual sales, production, and inventory data from the past month. Once the new forecast has been authorized by sales and marketing, it is applied to last month's operations plan. Once this is done, it is easy for the operations people to see where the operations plan needs to be changed and where it is acceptable. The necessary changes are then made that produce the new operations plan. The supply planning phase is where the capacity planning activity and resource planning takes place. The new operations plan for each product family grouping is compared with any changes made in the sales forecast or changes that have occurred in inventory or customer order backlog levels. It may be necessary to modify the operations plan if, for example, demand exceeds supply by a margin that is too large to reach with the current plan or vendor capacity. In cases where a change in the operations plan is necessary, spending authorization by top management may be required. These are the types of issues that are carried into the next step, the pre-sales and operations planning meeting, the purpose of which involves representatives from the various business functions. And here they make decisions regarding the balance of demand and supply. Also, they could resolve problems where differences in recommendations exist, areas that cannot be resolved to be discussed in the executive sales and operations planning meeting, developing alternative courses of action, and setting the agenda for the executive sales and operations planning meeting. This meeting includes a review of the plans for each product family grouping, the development of an updated financial view of the business, recommendations for each product family, recommendations for changes in resource requirements, and recommendations regarding alternatives needed to be discussed in the executive sales and operations meeting. The last step, executive sales and operations planning meeting, is the culminating meeting each month, and it includes the senior executives in the business. Its purpose is to make decisions on the sales and operations plans for each product family. Also, to authorize spending for changes in production, procurement rate changes, etc. Relate the collective impact of the dollarized version of the product groupings, sales and operations plans to the overall business plan. Breaking ties in areas where the pre-S&OP team was unable to reach consensus. And also, very important, to review customer service and business performance. To illustrate the nature of the sales and operations planning decisions, let's now see an example based on a company with a seasonal sales pattern on its make-to-stock products. We will raise the issues in the context of a single product family produced in a dedicated production facility. This figure shows the aggregate sales forecasts for our example, a product family at a company for 1 year. As you can see, monthly totals vary from a high of $15.8 million to a low of $7 million. Here, this chart shows these monthly sales data in the form of a cumulative chart display. You can see here the solid line. In addition, the dashed straight line represents the cumulative production if we chose to produce a constant amount each month, and that amount was calculated so that we would produce exactly what we need over the next year. The cumulative chart shows clearly the implications of alternative plans. For example, the vertical distance between the dashed line and the solid line represents the expected inventory at each point in time. If we choose to produce exactly the same amount as what we expect demand to be each month, we would not expect to carry any inventory. This unique policy is called a chase strategy, where production output is changed to chase sales. The opposite extreme is the level strategy, where production is at a constant uniform rate of output with inventory buildups and depletions over the planning horizon, and it is shown by the dashed line in the graph. Changing production output incurs the costs of changing the workforce levels, hours worked, and potentially subcontracting, if some subcontracting is being used as an option. Keeping production at a constant rate incurs inventory holding when cumulative production is greater than cumulative demand, and backorder costs when the opposite is true. The more typical way of displaying the sales and operations planning information is to use time-phased planning and a tabular display. The advantage of this approach is that it is easily captured and communicated using a spreadsheet. This information can be used for two important management purposes: evaluating current performance against the sales and operations plan, and modifying the future sales and operations plan. In the next couple of lectures, we are going to see this spreadsheet displays for those two types of strategies. Alright, let's continue with the lecture. This is an example of the tabular or spreadsheet displays. And this type of displays require several important information inputs each month. The sales forecast, here you see operations plan, inventory plans, and also actual operating results for the past 3 months here. The information used for assessing current performance is shown in the history portion of the report, and the plan for the future is shown in the plan portion of the report. In the sales section of the report, shown here, a planning factor of $30 per unit is used to convert sales dollar to units of sales. This statistic would be obtained from accounting records and represents the average value of a unit sold. Similarly, in operations portion over here, an employee productivity factor is used to estimate the required number of employees needed to produce planned production. In our example, it is assumed that 8 units a day can be produced by each employee. In the inventory section, we see a days of supply figure. Here. This is calculated by finding the expected sales per day for the next period and dividing that number into the expected end of month inventory. In the history part of the report, actual sales and inventory level are used, while in the planned portion, expected values are used. For example, in December, actual ending inventory used is 215,000 units. And planned sales are used. Here we have 253,000 units, which is divided by 20 days. So here, as you can see from the formula, the days of supply at the end of December is 70, rounded. And finally, the customer service numbers shown in the history portion are reported from an external source and not a calculation from report data. The actual plan shown in the figure depicts a chase strategy, where we plan to make the forecast demand for each month. Note how much the plant production changes each month and how the number of needed employees varies. This is the plant production and employees. The reason that there are only 10 working days in July is due to a planned 2-week summer shutdown that occurs every year at this plant. Whether this plan is feasible or not would depend greatly on the availability of workers that could be shuttled in and out to meet the widely varying production requirements. We will discuss this plan relative to cost later in the lectures, but note how hires and layoffs are calculated based on the changing number of workers from one month to the next. In revising the plan from month to month, the recent history shown in the report can be quite valuable. Here we see the recent history covering the last 3 months of sales, production and inventory levels for this product line. See, in that case, the actual sales have fallen short of the forecast sales each month during the past quarter. This is indicated as a negative difference. Difference month and difference cumulative here, and amounts to a cumulative difference of minus 100,000 units, or about 40% of the January sales forecast as of the end of the last quarter, as shown in the table. This trend in sales indicates the need to focus on reforecasting to better estimate sales during the demand planning phase of the sales and operations planning cycle. Moreover, the actual production has exceeded the operations plan every month during the past quarter, and the cumulative difference equals at plus 115,000 units. The fact that actual sales are less than the sales plan and that the production has exceeded the operations plan in each month has produced a major increase in finished goods inventory. As shown in the picture, the number of days of supply has increased from 3 to 17 over these 3 months. These results signal a need to adjust the operations plan to bring sales and production into balance. There are many ways in which this could be accomplished. One way would be to reduce the January production plan in order to bring the inventory level back to a reasonable level. It does not appear that our current plan does this. Also here, it's very important to see that there is some more data below, and especially costs and the total cost of this plan. In the next lectures, we will consider the basic trade-offs involved in developing the sales and operations plan and evaluate these trade-offs based on those costs. So we'll continue in the next lecture with the Chase Demand Operating Plan. Now here in this spreadsheet we show a chase strategy that is a little bit more intelligent than the previous one we talked about in the previous lecture. And here, rather than just producing expected demand each period, we produce at a level that allows us to maintain a target days of supply inventory level at the end of each month. This can be useful because the days of supply inventory level target can ensure that we have enough to cope with uncertainty in demand, but not produce an excessive amount. So here we show a plan that maintains 5 days of supply at the end of each month. Here you can see this is the target dates of supply. The trick here to calculate this plan is to first calculate the required ending inventory balances for each month that represents 5 days of future supply. For example, in February, we expect demand to be 280,000 units, or when we divide it by 21 working days, it gives 13,333 units per day. So 5 days of supply would be 66,666 units, which is our inventory target here for the end of January. Here you can see the calculation. Afterwards, the operations plan for January is calculated by taking the expected demand, then subtracting beginning inventory, actual in this case, and then adding the needed ending inventory, which gives 105,000 units. Doing this for each month allows us to find a chase type operating plan that results in a 5-week supply of inventory at the end of each month. And here is a short summary of a chase strategy with a 5-day of supply target. There are 4 steps. First, calculating end of month inventory target values, and you see the formula. Then calculating the operations plan in units. Step 3, calculating the number of employees required. And then calculating hires and fires each period. You can use this and all other spreadsheets. They are attached to the lectures, so you can use them and you can change the numbers and play around. We'll finish with this strategy and we will continue with the next one, which will be the level operation strategy. So the next basic strategy that we will develop is the level strategy or level operating plan. Here we are looking at the exact opposite extreme, where we keep a constant workforce for the entire planning horizon. So this is that type of plan shown here. So in this case, the labor force is kept at a constant 2,153 employees. Of course, the trick in this case is to figure out where this number came from. We do this by figuring out exactly how much we expect to need to produce over the planning horizon, and then divide this by how much one employee can produce over that same period of time. For our example, the forecasted demand over the 12 months is 4,333,333 units. This is the forecasted demand. We can subtract out our beginning inventory of 200 and 15,000 units, but we need to add back the inventory needed for our days of supply target at the end of the planning horizon. From our analysis in the previous lecture, we know that we need 66,667 units at the end of December. Here is the end of December target. So in total, we need to produce those 4,300,000 minus those 4,033,000 and so on thousand, minus 215 plus this 66 and so on. So we get a number 4,185,000 units. We know that an employee can produce 8 units a day, and we will work for 243 days over the 12 months. This is the sum of working days from January to December, 243. And an employee can produce 243 multiplied by 8, 1,944 units. So from this we can calculate that we need this exact number of units. Employees. So we round this to 2,153 employees. After calculating the number of employees needed, we can then fill in the rest of our table by calculating planned production, planned end of month inventory, and planned days of supply. Also, here we have the total cost of this strategy. You can use this spreadsheet, so it is filled with formulas, everything is automated, so you can put various numbers and everything is calculated automatically here. This is a quick summary of this level strategy with a constant number of employees and an end of the horizon days of supply target level. So we first calculate the number of employees needed, total production required. We see the formula here, planned production, employees required. And in step 2, we calculate ending inventory levels and days of supply. This example shows the basic trade-offs in operations planning. In our example, we focused on 2 alternatives so far, where the first required hiring and laying off workers based on meeting required demand, and the second required inventory accumulation to allow a constant complement of workers. Other alternatives that may be considered as well are undertime and overtime options and alternative capacity forms such as outside contracting. Evaluating these trade-offs is a very firm specific. In the next lecture, we are going to see how we can evaluate different types of plans and how to find the most optimized one. Alright, let's continue some evaluation of those plans we just talked about. So to illustrate this analysis, if we have cost data, so we use the same cost data that we used for the previous 3 lectures to develop different operations plan. So here we have, as you can see, the cost to hire an employee, laying off cost, also inventory carrying costs, beginning inventory, beginning labor force. Here we assume that the current actual employment status is 1,437 employees in January. Inventory is 215,000 units. And here we have captured the costs associated with the chase strategy from lecture 3, and also the level strategy, lecture 5. Here we have the total cost. With these plans, we assume that the total amount produced is the same with both plans because we start and end with the same amount of inventory and produce to meet the forecast demand. Given this, we have not considered the actual cost of production and only calculated the incremental cost of hiring, laying off, and carrying inventory. From this analysis, the chase plan looks like the winner, at least from the cost data analysis. So the last alternative, which we see here, is the mixed plan, and which we will show in a while here. It is a mixed strategy needing to add employees in April, July, and August, and laying off employees in December. April, July, and August, and laying off. In this strategy, we plan to carry the 5 days of supply at the end of December, as was done in the other two plans. In this plan, we have some periods when the inventory is being drawn down, January, February, and March, here, and other periods when inventory is being built in anticipation of future demand, August and October. As can be seen, this strategy looks attractive due to its low cost. It is much lower compared to other two strategies. Developing that kind of mixed strategy is probably best done using a trial and error approach based on the actual situation and options that are available. If labor flexibility is needed, it may be possible to have a temporary labor pool that is available during certain times each year. For example, during the summer, college students may be available, and it may be possible to take advantage of this talent at fairly reasonable cost. Many companies use temporary labor pools during certain peak demand times of the year as part of the operation strategy. Setting up a spreadsheet that allows trial and error testing of ideas can be done with equations similar to those we used for the chase and level strategies. A key decision that must be made is deciding what will be the decision variables. Decision variables are those cells in the spreadsheet that can be varied as part of the trial and error process. In the case of the mixed strategy spreadsheet shown here, the decision variables are the hiring and laying off decisions in January through December. The spreadsheet is designed so that changes in these cells are tied directly to the number of employees row in the operations part of the plan. So, for example, if we have 554 employees in April, here, this is reflected in the number of employees in April being 554 more than March. Plant production is then tied to the number of employees by multiplying by employee productivity and number of working days in the period. Then inventory is calculated by taking the inventory from the previous period plus plant production and then subtracting forecast sales. This solution here was actually found by using the solver optimizer that comes with Microsoft Excel. In the next two lectures we are going to see a real practical example, and we will show how to set up this solver and make best decision to find the most optimized plan. Alright, let's continue. So in this next lecture we present an application of advanced production planning models. So this case, ABC company has been developed to demonstrate the role of production planning models in the sales and operations planning process. There are some ways included. A company might estimate the necessary parameters, the additional information that might be generated in a sales and operations planning meeting, and the construction and the use of the model. Also, this spreadsheet and all other spreadsheets included in the course, you can download them from the resources section of the lectures. They are prepared. They have formulas, everything that you need to make your own calculations, to use it for practicing those calculations. So feel free to download it. And let's start first with this company. It's a fictitious company, ABC company, which is a medium-sized producer of equipment. The company makes 4 product lines, products A, B, C, and D. Its products in general face a seasonal demand and have historically been sensitive to overall economic conditions. ABC has a positive reputation for product quality and customer service in the industry. So despite the recent economic downturn, it has been able to show sales growth and profitability in the last couple of years. Also, the sales team expects a significant recovery in the economy and is very optimistic about sales for the next year. So in this table over here, you see sales, costs, and profits for the last 2 years. But there are also some clouds over those rosy expectations for sales growth, and it was the occurrence of some product shortages last year. These shortages occurred even though manufacturing used overtime to try to keep up with demand. It was the first time that the company had ever needed to put any of its products on back order, and even though the back orders were filled quickly, there was still some concern that its reputation for good customer service could be negatively impacted. These issues persuaded the ABC's company management to consider more formal planning process to help meet the increased demand. Up to this year, ABC annual planning had been quite informal. The process consisted of gathering forecast information and establishing budgets for the fiscal year. Once the budgets were established, external events such as big customer order or cancellations would trigger informal meetings where plans would be adjusted, reduced time or overtime would be authorized, and other adjustments. In the meetings about preparing for the next year's selling season, there was general agreement that back orders should be avoided if possible, and that more formalized meeting during the year might be helpful. Management also agreed that it would be advantageous to evaluate a formal planning model as part of the budgeting process and as the basis for the subsequent meetings. Though there was general agreement to proceed with the development of a planning model, there was little agreement on what approach to take, whether to hire a consultant, how extensive the model should be, and other details of the approach. Many of the company's managers and their contacts recommended an aggregate production planning model formulated as a linear program. Finally, the end result was an agreement to focus on aggregate production planning to determine staffing levels, to provide sufficient inventory to avoid back orders, to develop an in-house linear programming model of the process, and to assign a young manager to assist in the model development and subsequent analysis. The linear programming model that managers develop can determine aggregate inventory levels, direct labor staffing levels, and production rates for each month of the year. The objective function minimizes direct payroll, overtime, hiring and layoff, and relevant inventory costs. This model also incorporated the desired inventory level for each month and the direct labor force at the end of the year. So now we will avoid the theory behind such linear programming model and we will continue with the example in practice how this can be done. So now let's continue with the developing parameters for this model. In the early stages of the development, management decided to use the actual sales data for the current year. This would give them a known base and might also provide some insights into what they might have done differently to avoid the shortages that incurred during the last year. Also, in addition to the sales data, they needed estimates of the other parameters for the linear programming planning model. Alright, so the workforce strategy might be described as a one-shift level work strategy with overtime used as needed. At the time the model was being developed in the current year, a total of 93 employees worked at the plant. These employees included 52 workers on the assembly lines, 6 floaters, 20 workers in the machine shop, 10 maintenance workers, and 5 office staff. Even though the employment level of the direct workforce, assembly and machine shop workers, may be varied over the course of the year, the company tried to keep it as level as possible. The company is not able to do this exactly due to turnover and short-run production requirements. There is, however, very little turnover for the office staff and the maintenance group. Overtime is used when a regular time cannot meet production requirements. The plant is unionized, and relations between the union and the company have always been good. The company had access to good direct labor skills and provided a comprehensive training program. It is estimated that the total training cost in the current year was $42,000. Using these and other factors, overhead, personnel screening, and so on, the personnel officer estimated it cost $800 to hire a new employee. The personnel officer also estimated that the cost to lay off an employee was $1,500, including the severance costs and supplemental unemployment benefits. The 6 floaters are kept on the workforce to fill in for people who are absent, especially on Mondays and Fridays. They also help train the new employees when they are not needed for direct production work and often perform some administrative tasks. There was some discussion about how to treat those floaters in the planning model. To be conservative, the decision was to not consider them as producing employees. This would compensate for absences, new employee training, and the time they spent in the administrative tasks. This meant that even though there are 78 direct employees, only 72 would be considered as production employees. Since the model was an aggregate planning model, an average aggregate product was to be used, so an average cost of direct labor and labor productivity were needed as parameters in the model. So the average labor cost per direct worker was calculated to be $1,828 per month, using a 12-month planning horizon. The average productivity for the assembly and machine shop workers combined was 83 end product units per month per employee on a regular time. Due to union restrictions, a maximum of 17 units could be produced per month per employee on 4 8-hour Saturdays at this productivity rate. Based on this information, the labor cost per unit on regular time for the combined assembly and machine shop units was $22.3, and the overtime labor cost per unit was $33.4. Finished goods inventory was used to buffer against the uncertainties, to decouple production and sales, and to accommodate the cycle between models on the assembly line. When the company was out of stock, any sales were back-ordered and filled from the next available production run. In an effort to avoid the back orders that were incurred last year, the management decided to establish a plant minimum inventory of 2,000 units for each month. The determination of the cost of carrying inventory required estimates from nearly all of the management. The cost of capital was on the order of 10%. The direct cost of storage, space, lights, wages, and so on was estimated to be about 4% of the amount, and the design changes that were some obsolescence, which was estimated to be about 3%. Thus, a total of 17% of inventory value was to be used for the carrying cost per year for inventory. The average unit produced in the current year had $94.62 in material costs. The current year mix of regular and overtime resulted in $30.67 in direct labor cost. Thus, the average inventory carrying cost was estimated at $1.77 unit per month. The actual sales starting conditions and ending conditions were the only other data needed for the planning model. The actual monthly sales for the individual product has been totaled to provide the total aggregate sales for the company during the current year selling season, which is shown in this figure here. Also shown are the beginning aggregate inventory level and the beginning employment level of ending inventory and workforce age for direct workers. Also here we have the closing aggregate inventory level and the actual direct workforce of 72 people. Using these data, the planning model could be run to determine the improvement in operating costs that could be obtained with the linear programming model. Once this was accomplished, additional work could be initiated to apply the model to the forecast for next year's selling season, so that these improvements could be obtained in the coming year. So here also we have calculated and determined the cost base against which to compare the results of the planning model. This table shows the aggregate sales, production, inventory, workforce, and overtime production actually achieved in the current year. By applying the planning cost parameters to these data, a cost basis can be developed for comparison with the linear programming model results, which we will see later. When the planning costs are applied to the actual current year's results, the total annual cost is $2,562,925. Here we have the regular time costs, inventory carrying costs, overtime, hiring, and firing costs. So this should be firing costs here, not hiring. Firing and hiring costs. So this is the information for the cost for the current year. Now, in the next lecture, we continue with Solver and how we can optimize this model. Let's continue with the solver solution of this problem. So the table shows the aggregate plan here. We have the decision variables here in regular production, overtime production, workers hired and fired, ending inventory in each month is calculated by beginning inventory plus regular production plus overtime minus forecasted demand, and the ending inventory for a month is the beginning inventory for the next month. Similarly, the workforce level for a month is calculated by previous month workforce level plus hires minus fires. These are often called balance equations by those familiar with setting up linear programming models. Maximum regular time production is calculated by taking the workforce level and multiplying by the number of units produced by a regular time employees per month. 83 in this case. Overtime production, similar way, using the overtime maximum units per employee, or 17 units. These maximum levels are needed for setting up constraints that limit regular and overtime production. Solutions are evaluated by calculating the total cost of the solution. Here we have the cost. Hiring cost is the sum of the number of employees hired during the year multiplied by 800. Firing cost is the number of employees fired here multiplied by 1,500, which is the cost. Then we have workforce regular time cost, which is the number of regular time employees over the year multiplied by $1,828. And then we have inventory costs, which is the sum of the ending inventory levels multiplied by $1.77 per unit per month. And then we have the total cost. So here we have a number because we have input formulas, but when we solve, this number will be changed. So now we have to set constraints and other parameters. So we access solver from data here. So here are the parameters, and we will explain them shortly. First, the target cell is set to be G25 and equals to minimum, because we are looking for the minimum cost. This tells solver to minimize the value calculated in this cell, which is the total cost. Next, by changing variable cells, specifies the decision variables in the model. So we can change two values in the blocks of cells, D10 at 21, H10 to I21. These are the regular and overtime production which is put into the model, and the block of cells for hiring and firing numbers. By specifying these cells in by changing cells, we are telling the program to determine the minimum cost solution by varying only the values in these cells. Next, we have to set the constraints need to be specified. We will specify 6 constraints. The first constraint forces the August workforce level to 72 employees. The second requires regular time production to be less than the maximum regular time production. Second one. The third states that overtime production must be less than maximum overtime, which is set by the legislation. Next, we need monthly ending inventory level as to always be equal to or greater than 2,000 units, which was agreed by the management to keep the inventory level minimum at 2,000. And the fifth constraint forces ending inventory equal to 16,460, which is also set by the model. And finally, the last constraint requires an integer number of employees. Now, when we press the solve button and keep the solver solution, we will receive the total cost of this model. Now, when we see the total cost, we got from the solver, we see that there is a difference or savings produced around $207,000, which is 8.1% of the production planning related cost for actual operations, compared to actual results from the current year. This is from this table here, right? So, in reviewing the differences between the linear programming results and the actual operating results, there are several conclusions. First, substantial overtime was incurred by the plant to meet the actual sales demand. You see overtime costs. Here is zero. Here is almost $180,000. Also, the employment-related cost of regular and overtime, we save $66,000. And the main difference also is that while substantial overtime was used in actual operations, the linear programming model used regular time production capacity instead of overtime to produce nearly all of the product units. And second, the employment level was adjusted each month, hiring and firing employees as required to meet the actual sales demand. This resulted in hiring and firing costs. Here you see almost $112,000. In contrast, the solver model made small adjustments in the employment level in February and August. Maintaining a relatively constant workforce throughout the year because of the magnitude of the hiring and firing costs. And we also see here the difference. Third, the LP model was also able to provide a small reduction in finished goods inventory and still meet the inventory goals of the company. Very, very small reduction. Many of the cost improvements are related to implementing an overall sales and operations plan as opposed to reacting to monthly variations in sales and customer back orders. Reducing the level of system nervousness produces a better balance of costs in managing operations. Clearly, the overall cost of operations is affected by the planning assumptions regarding the employment level and the ending inventory targets at the end of the seasonal cycle. In this case, ending figures for August for the current year. Different assumptions regarding the appropriate level for employment and inventory can change the overall cost of operations. These assumptions are heavily influenced by executive judgments regarding the sales forecast for the next year and the level of safety stock inventory needed to achieve the level of customer service required by the market. Such judgments are discussed and agreed on by senior executives in the company's sales and operations meeting. The sales and operations planning issues raised by the executive at this ABC company can be resolved using a planning model such as this spreadsheet model or using Solver, and planning meetings can be focused on decision making by senior executives regarding the important trade-offs issues between the various functions in the company.